All right. All right, Vitali, I will change your status as present. Okay. So think like this. So we have then this lab 4, which is going to be on lenses. All right. So we have um, two types of lenses that we will be, working with. Generally, when you're talking about lenses, there are um, two types of that, you know, let's say, or, two major types, which is, a flat lens, let's say, maybe something like this, right? Maybe like I don't know, maybe like, let's say a block like that where the light can go through, something like this. But this is not something we're considering. We're going to consider a curve lens, and there are two types of curved lenses. So there is a concave and convex. So concave and convex, and concave convex have, kind of like very similar to the mirrors as well, sort of like a shape. So the concave, concave one is shaped like this. So like, let's say this is the shape of the lens. So then the convex then shape sort of like this. So concave, convex, those are sort of like the curved mirrors. Sorry, curved lenses. Things like this. They are, you can think of, is part of a, sort of like a sphere where, sort of like if you take it and kind of carve it, sort of, so carve sort of like one piece like this, so that becomes sort of like our convex. Okay. Or if you take it and, carve it like this, that becomes basically concave. But sort of like coming from similar, like, let's say acrylic or glass, sort of like, let's say a shape. Okay, so in terms of then what we can think about here is our goal will be to find an image for a concave lens and for the convex lens, and sort of like, let's say, look at some of the characteristics of each lens. What type of image can we get? um, Remember, in terms of when we talk about, like, let's say image, right? So we put some object in front of the lens, just like we did with the mirror, and then we can find, let's say, the image. Now, one of the things we can think of here is sort of like, let's say, let's start with the convex. So convex, sometimes also known as a converging lens. That's because when you have, let's say, for example, a lens like this, and let me sort of like draw a optical bench like that. So when you have a lens like this, so let's say you have an object. Remember, so we have this object. Let's say the object is, I don't know, let's say, for example, really far away, which means that the light coming from the objects will be sort of like parallel to one another. So the light basically parallel to one another and moving parallel to the optical axis. All right. So when this light comes in and hits the mirror, hits the lens, again using the law of reflection, or also, Snell's law. So we can see that it hits the lens at this at this position where, maybe let's say that the normal will be something like that. So then it's going to bend toward this normal, and then here it hits this other surface, bends away from the normal, and actually you're going to move like that. Okay, so you already can see there's a big difference between lens and a mirror. Mirror always reflects all the light in the same side as the incident light. That means you have a incident or incoming light hits the mirror and then reflects in the same direction, in the same side. Lens allows the light actually to propagate to the other side. So then what you're looking here is there is incident and there is a refracted light. So there is a little of reflection. There's going to be a little of reflection. But at this point, when you're dealing with lenses, remember, with the mirror, everything is reflected, and that's the light that we technically care about. Lenses, we don't care about the reflected light. We only care about the ones that propagate. So basically, reflected light. We only care about the refracted light, only the one that goes to the other side. All right, so this one will come in, hits the mirror again, same thing, right? Sorry, lens. So it will deflect again, deflect, and kind of go like this. Same thing with this one, will go like that. This one will actually go straight. This one kind of going to go like this. And what we will see here is that the light will actually converge at some point. Refracted light. That means the light that goes to the other side. That's why we have the name of this convex lens also as a converging lens, because the light converges to some single point. Obviously, the light doesn't stop there. Each light, the ray kind of continues, but that is the point where they converge. Now, what I have here is that will be then the position of my image. That will be then the position of my image. So if I then measure the distance from the center of the mirror, so center of the lens, so like to that position, that will be S prime, which will be then the, remember, I think like S prime is the image distance. That's the image distance. Okay, so now in terms of then what we want is to relate those quantities, image distance, object distance, right? And the last thing we have here is we also want focal length. Focal length. So those three things should be related to one another by an equation that you already seen before. This is known as a mirror equation. That was what I showed you for the mirror lab last week. But technically that same equation now can be called a lens equation, where 1 over distance plus 1 over object, 1 over object distance plus 1 over image distance, then is equals to 1 over focal length. Exact same equation can be applied to what we call thin lenses and for the mirrors. Okay, so as I mentioned, right, object is really far away, or we can say it's infinitely far away because the incident light is parallel to one another. So if I come back and sort of like, let's say, rewrite this equation where I have 1 over infinity plus 1 over S prime equals 1 over F, we can see that this whole term goes to 0. And then what I have is that 1 over S prime equals 1 over F, or S prime is equals to F, which means the same position where we find the image, assuming that light coming from infinity far away, is also considered to be the focal length of the lens. Okay, that means the image position is same as the focal point, pretty much. So then that distance is then focal length. That means I can say that this distance is also my focal length of this converging or convex lens. Right? Any questions? All right. So now, in terms of some of the important things to remember about lenses, which was also true for the mirrors. Remember, there is a positive side and there's a negative side. Okay, so for the mirrors, what we did always, the positive side and a negative side was basically in terms of where is the outgoing light, and the side where we have the outgoing light was then the positive. The side where you don't have outgoing light then is the negative. So as you can see, for the convex lens, the side where the light is outgoing is the back of the lens. Okay, so that means I can say that this side here is my positive side, and obviously the side, the front of the lens is the side where the light is not outgoing. So then this will be then the negative side. Okay, so for this for this lens, right, a convex or converging lens, then positive is basically where the outgoing light is, because the light refracts, right, goes to the other side. So that's going to be our positive side. That means, for example, if your image is located same side as your positive side, then image distance will be positive. Well, since focal point is also at that side, right? Then you can say also focal point is also positive focal length. So let's say for that particular one, right? And what you have here is, so you have this, focal length is positive. And put like this: focal length is positive, and image distance is positive because, for example, for that image is the same side as the outgoing light, so it's positive. Okay. Well, one thing we have is that, remember, there was also radius. So technically, then there's all, you can also talk about this, but lenses technically have you know, two radiuses, right? So you have this shape like this, which considered to be part of one sphere, and this one part of another sphere. And technically, you have, a radius 2 and a radius 1. So radius 1 is positive, radius 2 here is negative. And the one that is positive is the one that interacts with light first. So you can say, right, this second, this sphere is interacts with the light first. So then you take that to be radius 1, and it's positive. Okay. All right. In terms of then concave lens. All right. Oh, by the way, also in terms of the image, remember, image that generates by mirrors or lenses can be two different types. You can have a real image or a virtual image. Okay, so would this be a real image or a virtual image? What do you guys think?
Real.
Real. Why is it real?
Because the light passes through.
Yes, because actual light goes through that point where we call our image. Exactly. So in this case, the image here is like this. It's real. That means when you have actual light rays converging to some point and generating the image, that's basically a real image. You can also say this: if the image is on the same side as the positive side for your system, then it has to be a real image. Okay. Now, in terms of, then we have a concave lens, which is shaped like this. So it's shaped like this. So let me do this. Right, shaped like that. So we draw this line over here. Okay. So now think like this. Again, what we have here is object has a position infinitely far away. That means the line, the light that's coming from that object parallel to like this. All right, so this guy gonna come here, hits the lens, go into the lens, and then come out like this. This one gonna come in, hit the lens, gonna come out like that. This one gonna go like that. This one gonna go like this, and so on and so forth. So let's ignore this one for now. As you can see, right, the light, outgoing light, will be diverging in the back of the lens. That means what you have here is that if you look at all those outgoing lights, right? So let's say ray 1, ray 2, ray 3, and ray 4, none of them will be converging to, intersect with another, another ray. All of them are diverging away. Now, how do we find the image? Well, we take those outgoing lights, ray 1, 2, 3, and kind of, virtually trace them back. So virtually trace them back. And then where they virtually converge, then that will be image distance. Okay. So that's where the image is for a concave lens. Again, remember, our positive side is still this side here, right? Because it's the side where the light is outgoing. And then the negative here. That means, the negative is the front, positive is the back of the lens. Again, if I use this equation, 1 over s plus 1 over s prime equals 1 over f. Since this is infinitely far away, this is 0, so s prime is equals to the focal length. So this is, how we find focal length, by basically finding the image position. Okay. Now, this image is going to be in the back of in the front of the lens, which is the negative side. So image will be negative. Well, focal length is equals directly to the image. That means, it also will be negative. Okay. So focal length is negative and image is negative. Now, here's the thing. Those two things always true for concave lens. Always true for concave lens. Okay. That means you're always going to get negative image, negative image position and negative focal length. And if I'm talking about then the image itself, in terms of real and virtual, what type of image would this be? Real or virtual?
Virtual.
Yes, this one is virtual. And it's always going to be virtual. Now, there's one thing about concave lens is that you always going to get a virtual image. Okay. Now, if I go back to the convex lens, can I also say that image is always real for the convex lens? What do you guys think? Would that statement be true?
Yes.
Anybody else agrees with that? Actually, that's not true. Convex or converging lens can give you real image and also virtual image. Okay, it can give you real image or virtual. It can also give you this, no image. All right, it can also give you this. And the conditions, probably you should, check your lecture notes or lecture videos. So the idea here is this. See, what we did, we looked at object that is really far away, which was, let's say, infinitely far away. Okay. Now, as long as the distance, let's say object, let me do it like this. As long as the object distance is from infinity all the way to, as long as it's like, let's say, less than, I put it like this, focal length, less than focal length, the image is real. When object distance equals to focal length, let's see what we get. Let's look at this equation over here. 1 over object distance plus 1 over image distance equals 1 over focal length. Then 1 over image distance equals 1 over focal length minus 1 over object distance, right? But see, if object distance is same as the focal length, then I can say this is 1 over f minus 1 over f, basically, which is pretty much 0. Well, then if I have then 1 over s prime equals 0, which means s prime here is infinitely far away or undefined. That means you can't find any image of that. It's infinitely far away. Its image is at infinity. That means when the object is placed at exactly focal length or focal point, right, you will see no image. But then as you move the object even closer to the lens, that means distance is less than focal length. Sorry, guys, here I have a, like this. Okay. That means it's real as long as the object distance is greater, or, let's say, I guess maybe like this, less than or equal infinity. So basically it's infinity or getting closer and closer and closer. Sorry, I had those symbols wrong. So that if object distance from infinity getting closer and closer and closer and closer and closer to the lens, as long as it's from infinity all the way to less than focal length, you get a real image. When it's placed at the focal length, you get no image. When it's even closer to the lens than the focal length, then your image is actually virtual. Okay, your image is virtual. So you get really interesting cases with the convex lens. So that's why saying that the image always real for the convex or converging lens will be false. It gives you a real image, it gives you a virtual image, it gives you no image, depending where the object is. Going to the concave lens, it doesn't matter where the object is. Your image will always be virtual, right? It always be virtual, regardless where the object is. And generally, virtual images are upright, where the real images are upside down. So, in a way, the concave lens gives you only one case: virtual image, upright, and always actually smaller than the thing like this. It's also smaller than the object. So smaller than the object. So in a way, you can see, right, there's a virtual image generated by the convex lens, and there's a virtual image generated by the concave lens. The question is that how do we separate those? How do we know which one is what? When you see a virtual image, how do you know if it's concave or convex? Well, virtual image generated by the concave lens always smaller. Virtual image generated by the convex lens is always larger than the object. So that's why this is the magnifier. Convex lens gives you the magnifier, right? Magnified, much larger image. All right, so that's kind of like what we have for this lab. Any questions? All right, so if you go back here, so this is what I have. So this is on Pivot right now, concave and convex lenses. So our objective is to discover the rules that determine how rays of light change direction as they pass through the concave and convex lens. So the experiment itself is very straightforward, similar to the previous, lab 3 experiment, where you have a laser used as a source, and then you have a lens. This is a convex lens. You can see, right? You have convex lens, concave lens, and scaling. We don't really need that. So let's go, let's say convex lens, and see what happens when you have a light incident and you can see, right, how the light bends, right, as it goes through the lens. And it bends even more when it goes toward the edges, right, toward the most curved side of the lens. All right, so your experiment should be very similar to what you did before. So let's say, I guess, put this here at the center. You can then use lines. So this will be your, one of the outgoing lights. Then you go and look at another outgoing light. So you put it here, turn it, place it there, and then, do the same with another one. So you need about, let's say 5 lines, 1 in the middle, 2 above, 2 below. So I'm not going to do all 5. I'll just show you from, let's say, from maybe like few. So let's say if I do this one, you can see, right? So let's say this one, here's the outgoing light, and you can see, right, what happens here, they all converge at that point. That's where your image is. So then what you do here is you take a ruler and measure that position from the center of the lens. Okay, so that's why this is a converging lens, because light actually, so this is my positive side. This is my negative side. Positive because those are outgoing lights. Okay, so this is where we have refracted lights. Okay, so since that's my refracted side, the refracted light, and I can see they converge, so that's why it's a converging lens. And this is a positive side. Image distance is positive, and let's say you can use that and find it in the focal length. Any question about this convex lens? All right, then we go to concave, and you can see, right, we get, so let me get rid of those. So we get now a different shape for the lens. And what I have here is, again, the video will show how the light would interact with the concave lens. And you can see how it diverges away. It, refracts to the other side. Okay. Then your goal will be to, again, sort of like, let's say, so take it, put it at the center, use it as a reference, then use some of those lines, right? So here's your line 1, which is you're looking at one of the outgoing lights. And then you look at another outgoing light. So do like this. Anyway, I think you got the point. So put it there. No, I don't think I did it correct. I think this is a little bit better. All right, so then go and maybe do another one on the other side. So again, you need to do 5, right? So you need to do 5, to get that. So then there's the other one. Put it like this. Anyway, you can see that more or less, I'm not, you need to be more accurate than what I'm doing. More or less, they converge here. Okay. Well, they don't really converge, right? So I had to virtually trace them back because the lights, kind of like diverge away like this. So they don't really, converge anywhere, those actual refracted light. So I virtually trace them back and then find the image position here. Okay, so virtually find where if you, let's say, trace them back, where would they converge? And that's, what we do is to find this particular, focal, image position and focal length. All right, any question on that? So after that is mostly, just kind of questions regarding on your experiment. And again, so here you just basically work on that. This one, you just sort of like, first one is observation and answer some of the questions based on that. And then here where, like, let's say, do an experiment where actually start measuring things. So determine the focal length. So here I need to I need to see all your work. Okay. So for example, the best thing you can do here is do what I just did, right? So I have the five lines, and experimentally, you have a video, right, where you have those lines and you show where they converge, and take a screenshot of that, and with a ruler right next to that. That means, more or less what I have here is, what I mean is this. So let's say those were like, let's say, your lines. So let's say those were your lines, and then say, all right, so whatever. So let's say they converge here. So you can do a screenshot of that and then include with the, let's say, ruler next to that. So, here's what I have. That's why the value is this, let's say. And then you can basically represent this as your experimental, proof of the image distance. Okay. And then you do the calculation for, let's say, the focal length and so on and so forth. But make sure to include the screenshot, right, of the image position that you measure. Okay. So that I can, when you say it's 5 meters or 5 centimeters or 500 meters, I have a screenshot to verify that.
Does Pivot save like what you leave the lines on as if you once you submit it?
It doesn't.
Oh,
That's
it doesn't.
why.
Okay.
That's why it's not like a graph when you can leave it like that.
Mhm.
It doesn't do that. So that's why doing the screenshot is the best way of me seeing what you did.
Okay, and then so I didn't do that for this the lab before we had previously. So is there like any points marked down for that, or just for
Um,
future reference?
I don't know if I mentioned that. Basically, if I don't think I did, so no point will be taken up for mirror lab. But definitely now that I'm telling you for the lens lab, right? I want you guys to do it because I realized myself when I was grading for another class for that lab that I don't have a way of looking, seeing your labs, seeing your work, right? For this part. So that's why if there's no, let's say, graph where I can verify, I'll start asking students to do screenshots of their, let's say measurements and things like that.
Okay, cool.
All right. Any other questions, guys? So again, so, right, the rest is just basically answering questions based on what you just did.
The screenshot, you want us to put that in a PDF and then submit it in Canvas? And
No,
do
no,
you
no.
want us?
See over here.
Oh,
For
at the
number
picture.
one, there's a like you can use this to upload a picture.
Yeah.
Make sure that your picture is small file. Try to, like, in your computer, like maybe convert it to small file, or when you take in a screenshot, or I think if you're using your computer to take a screenshot, you can find a way to make it really small. But yeah, use that button to upload the picture directly. You don't have to convert anything to PDF.
So you go into Pivot to grade everything?
Yes, everything will be done on Pivot for this lab.
Gotcha. Thank you.
Okay. All right, anything else? All right, guys, so then let me spend the rest of the time, we have like about 20 or so minutes.